Okay. I don't know if, hopefully the audio is working. Let me go ahead and open up the live terminal here. Sorry for that little hiccup. Let's see. There we go. All right. Thank you, Reed. There we go. Sorry about that. I don't know why the audio is not working on this mic, or it's probably just the crappier mic now. Unfortunately, there we go. Let's see. Thank you. And there, hopefully that is, thank you, Nicholas. It's working now. Excellent. All right, so anyway, we're going to be going over big O asymptotics today. We've already gone through the analysis, the 5-step process of where you identify the input, you identify the input size, you identify the elementary operation, and you find, and then finally you analyze it with respect to how many times is that elementary operation executed with respect to the input. Now this is the 5th step, where you characterize that function with respect to a big O analysis. We kind of hinted at it up till now, where we're going to try to we're going to want to ignore the lower order terms. We're also going to want to ignore any constants, because those constants can be subsumed by improving your hardware. You have a computer that's twice as fast. That's going to be the operations themselves are going to be twice as fast, and therefore the constant sitting out front changes anyway depending on the hardware and the software that you're running it on. So ultimately, our motivation here is we want to characterize an algorithm on how efficient it is with respect to the input size, and we already gave that a name, n, right? We're gonna call all of our input sizes n, regardless of what they are. In other words, how does the function in step 4, right, grow with respect to n? In other words, for larger and larger n, what is the growth rate? So we're only really interested in n as n tends towards infinity, because for small input sizes, then we really don't care about the practical differences between two algorithms don't matter that much. In fact, if we focused on if we focused on just a range of small values, then we would have the misinterpretation that one algorithm is better than another algorithm. To show you what I mean by that, I've set this up. I've set up Wolfram Alpha here to graph two functions. Here's one function. It's a quadratic function, 100n squared plus 50n. And here's a second one. Let me go ahead and change it to simply just n cubed here. I'm going to graph it from 0 to 105. All right, so basically on the x-axis here, we've got the input size. The input size can be 0 up to of size 100. And if we only focused on this section, then we get the misimpression that the n cubed function here is better. Remember that the y-axis here is quantifying performance. It's quantifying the number of resources required to execute your algorithm. So lower is better. But anything beyond that point, 100 and greater, I think it's actually 101 or greater, something like that. Then clearly, if I mapped it out even further, then this n cubed would always be on top. It would be taking more resources than the n squared. And that's why we don't want to focus on small input sizes here. For an input size of 0 to 100, who cares what the performance is? Because we're interested in practically, we're interested in larger and larger inputs. We're interested in these two functions. Which one is bigger? Which one has a larger rate of growth as n tends towards infinity, as you move out for larger and larger inputs? And that's what we're interested in, okay? So again, if we only focus on small inputs, then we might get the misimpression that one function is better than another function, thus one algorithm is better than another function, when in fact it's not. So in addition, we don't want to have to worry about, as I said before, constants, right, or lower order terms, right? Because we're looking at it as n tends towards infinity, then all those lower order terms, they're still going to contribute some to the value of the function, but they're going to be completely eclipsed by the higher order terms. Those constants we don't want to have to worry about because, again, we can always improve our hardware and get those constants down a little bit more. So the way that we can achieve this, thus the tool that we use to characterize the rate of growth of resource functions. Remember, don't lose the forest for the trees here. Why are we doing this? Because we want to quantify algorithms and their performance. Algorithms require resources, memory, time, whatever, and we're just using those using this mathematics as a tool to capture those resources and to capture a notion of how many resources these algorithms actually take. So then we're going to use the tool that we use for this is big O analysis. Some people call it big O analysis or asymptotics. All right, so I'm just going to jump into it with a definition. And to do that, I'm going to go ahead and move over to my overhead here and double check that my mic is still working. Yep, it's still working. All right, so here's the actual full mathematical definition. So say that we've got two functions. These two functions are characterizing an algorithm, two algorithms. The performance of algorithm A can be characterized by f of n. The characterization of algorithm B can be characterized by g. All right, so we've made this really abstract by just considering functions now. All right, we say that f of n is big O of g of n, and this is how we read it. F of n is big O of g of n. That's how you should read that mathematical sentence there. If there is a constant, a positive constant c, and an n naught such that f of n is less than or equal to c times g of n for all n greater than or equal to n naught. Now this is a lot to parse out initially, but really here's the intuition. After a certain point, in other words, if you look at the graph again, after a certain point, these functions might, intersect. They might cross over each other several times. But at a certain point, what you can do is you can look at these functions, and this function will always be larger than this function, right? We don't care about anything that happened before, but at some point, that point being n naught, then this function is always going to be greater, g of n, is always going to be greater than or equal to f of n times some constant, of course, right? And that constant is not that important, but if you want to look at it from the graphic point of view, that constant is moving this, making this a little bit steeper or a little bit shallower, however you want to look at it, but it's not changing the order of growth because, again, we don't care about constants, okay? That's all this is saying, that at some point, you can definitively say that this function is going to be bigger than that other function forever, right? As n tends towards infinity, okay? That's what this definition is doing. It's basically saying that this function is no bigger than this function asymptotically. That this is the larger function. If you want to look at it that way, this is the smaller function. But when we say larger and smaller in this context, we mean their rates of growth. This function will have a larger rate of growth than this function. And since we've got less than or equal here, actually it's more technically correct to say that this function is at least as big as this function with respect to their order of growth, or that this function is no bigger than this function with respect to its order of growth. Okay, that's what we're looking at here. That's what the what big O. That's the definition of big O. So what we're going to do is we're going to go through several practical examples here of, all right, well, how do you use this tool to say that this algorithm is better than that algorithm, that this function has a larger order of growth than that function? All right, let's go back. make sure, check in with everybody. Yep, all right, everything's still running fine. All right, great. Again, if you want to, you can ask questions on Piazza. We've got a live Q&A session going here. I do have a LaTeX version of that definition that I'll go ahead and bring over. I thought it's not rendering currently in Atom using Markdown, so I'm going to have to, I'll put it in there just for the completeness of the notes, but of course I already wrote it over here a little bit better. And again, the whole purpose of this is that big O characterizes the function's order of growth as n tends towards infinity, as larger and larger n. It allows you to ignore lower order terms because you're looking at basically the limit. Now we don't require calculus in this course, so we're not going to talk explicitly about limits, but that's basically what it is. If you take the limit of a ratio of two functions as n tends towards infinity, then basically that's the real definition. We're using more of an algebraic definition, if you want, to consider it that way for this course, because we're not assuming calculus. It allows you to ignore constants because we don't care about that C sitting out front there. This C right here. We can change that constant to 1 billion. We can change it to 50 trillion. We can make it as small as we want. We can make it as big as we want. And ultimately, that's going to allow us to ignore those lower order constants. It allows you to focus on the most significant term in a function. And for that, we already have an intuition. If I gave you a linear function and a quadratic function, you could say, well, yeah, that quadratic function, that's going to grow a lot larger. If I gave you a polynomial function and an exponential function, yeah, you already have the intuition that that exponential function, that's going to be growing way faster than the polynomial function. If I gave you a constant function, that's not growing at all. That stays flat. And any other function, well, a logarithmic function. A logarithmic function is going to grow slowly, but it still at least grows. And so you have an intuition about this function versus this function, and which one is larger with respect to the order of growth. But now we're going to give you a tool to quantify that more rigorously from a mathematical point of view. Okay. Just some miscellaneous stuff here. So we can write that f of n is equal to O of g of n. And again, the way that you read that is f of n is big O of g of n. This is a little bit of abuse of a notation, but it's so common that I'm going to use it in this class. That's because we don't assume calc. We also don't assume discrete math, where you would actually write the in operation, because what this is a function over here on the left-hand side. This is a class of functions. That class of functions is the set of all functions that are ordered of that order. So if this were a linear function, it would be the set of all possible linear functions. Or it could be the set of all quadratic functions, or the set of all exponential functions, or something like that. Okay, but it's a little bit of an abuse of notation, but it's perfectly fine here. So again, the way the alternative, the real way to write this is f of n is in this set of functions, or this class of functions. And again, it's not going to render unless I explicitly render it here. So let me go ahead and toggle that preview and see. Let me show you what I'm talking about here. That's the proper way of doing it. This set notation right here. And here it is again, rendered as LaTeX. Maybe I'll go ahead and keep that up. I've got enough real estate here. I can go ahead and keep that up if you want. All right. But that's what we're looking at. Okay. The definition is not what we call tight. Okay. That it establishes a relative ordering of function rates of growth. Right. So, for example, that if I've got say a function n, that's going to be big O of n, right? That any linear function, if I go 3n plus 3, here's a, I'll go ahead and, since I've got LaTeX up here, 3n plus 3, that's big O of n, right? But also, it's also true that 3n plus 3 is big O of n squared, right? That's because this is just bigger, right? You're just making this the class of functions larger. Any linear function is still going to be constrained from above by a quadratic equation here, right? So it just has to be that the thing on the left-hand side is less than or equal to the thing on the right-hand side asymptotically. And of course, you can continue to make it bigger, right? 3n plus 3 is still going to be order of, say, 2 to the n, right? That's even bigger. That's going to be an exponential function. However, you can't go the other way around. 3n plus n or let's go with the squared, plus 2n minus 2 is not equal, NEQ for this, to order n. Here, and let's take a look at the rendering over here. 3 to the, this is the thing on the left-hand side here, that is going to be a quadratic equation. A linear function is not bigger than a quadratic function. So 3n squared plus 2n minus 3 is not going to be order n, right? So it only works in one direction. The thing on the left-hand side has to be bigger or less than or equal to the thing on the right-hand side. And again, I'm using the less than or equal to here in terms of asymptotics, in terms of rates of growth, okay? According to the definition of big O. So let's get our hands dirty a little bit here, and let's look at some proofs. All right. So there are a couple of ways that you can do this, but given two functions, f of n and g of n, how do you prove mathematically that f of n is order g of n? Right. And I'll go ahead and make sure that those are all LaTeXed up there. Right. In fact, I think I can increase the size over here so that it's a little bit clearer. There you go. No questions so far? No questions so far. All right, so, well, I'm going to go ahead and show you two techniques. First of all, approach A. So what I'm going to do is I'm going to jump back over here to the definition. We say that f of n is big O of g of n. If there's a positive constant c and an integer n naught, such that f of n is less than or equal to g of n for all n greater than or equal to n naught. So in other words, we've got two variables here, c and n naught. So if I've got two variables, what I can do is I can fix one and then find the other one, or I can fix the other one and find the first one. Right? And that's basically the two approaches that I've got. Approach A is I'm going to find the crossover point, where one function becomes larger than the other, right? And this corresponds to fixing c to be 1 and finding n naught, so that all n greater than or equal to n naught, the inequality holds, right? And as you can tell, that the approach B, I'll save the notes for next time here for this, but fixing C and then finding n naught, just the opposite. We're going to fix n naught and find a C that works, such that this inequality up here holds, right? So what I'm going to do is I'm going to go back to Wolfram Alpha over here, right? And here are my two functions again, right? Here are the two functions, and what I'm going to do is I'm going to expand out over here, and let's go ahead and look at this graph from a little bit higher, or not higher resolution, but we're going to zoom out from that graph a little bit here, right? Now, this graph actually, we've got a cubic function and we've got a quadratic function. They're going to intersect each other at 3 points because we've got 3 roots. That's all we're talking about when we're finding this crossover point. I want to find this crossover point, but there are actually two other crossover points. When one function intersects with another function, you can look at that as finding the roots of those functions, where you set function A equal to function B, and then you find the roots. What I want to illustrate that point, what I'm going to do is I'm going to transition over back to my overhead, and let's do it. Let's do the full proof by hand here. All right? So my functions, again, are f of n. Hopefully you can still hear me over there. F of n is going to be, what was it again? 100 n squared plus 50 n. Okay? I'm going to switch colors over here because this is a better pen. And g of n is n cubed. I kept things simple by keeping these two functions simple. Okay. Now, my intuition tells me that a cubic function is going to grow a lot more than a quadratic function. So we want to show that f of n is big O of g of n. In other words, to do this, we need to establish that f of n is less than or equal to some c times g of n. Well, we've already made a couple of assumptions here. That my first approach is going to be that I'm going to set c to 1. So that immediately disappears. And I simply want to find an n naught such that this holds. This inequality holds. That after that n naught, if you look at that graph, it was somewhere around 100. After that n naught, g of n is going to be larger than f of n. So to do that, what I'm going to do is I'm going to actually set these equal to each other. Right? So now I'm going to go ahead and take the actual definitions of these functions and put them in here. 100n squared plus 50n is equal to n cubed. Right? I'm going to bring everything over onto the other side. N cubed minus 100n squared minus 50n is equal to 0. And now that's in a form that should be obvious what you need to do. You need to find the roots of this thing. Okay? Now, finding roots of polynomials is well established, but I don't remember how to do it for cubics. There is a formula for it. A couple of formulas for it. But I chose these functions for a very specific reason, so that it would be easy to find these roots. First of all, you'll note that there's an n term on every single one. So one of those roots is 0. Those two functions intersect at the origin, basically. Okay. So I can immediately take that root out, and what I get is n squared minus 100n minus 50 equals 0. All I was doing was factoring out an n here, right? And I was dividing by it over here and just getting rid of it. Okay, that leaves me with a quadratic polynomial. Now I can use our old friend, the quadratic formula. The quadratic formula being negative b plus minus square root of b squared minus 4ac all over 2a. Where a is going to be 1, b is going to be negative 100, and c is going to be negative 50. Right? Well, this is not an algebra course, so I'm not going to do that. Instead, I'm going to go back and let Wolfram Alpha do it for me. Right? Here we go. So I asked Wolfram Alpha to find me the roots of n squared minus 100n minus 50, and it found two roots. Let's take a look at this first root right here, right? And it's in symbolic form, but that value is negative 0.49. Right? In other words, if I look back at this graph over here, the crossover point is somewhere over here. In fact, we can go ahead and zoom in on it. Let's go. We'll graph it from negative 1 to 0. And when we look at that, we see that crossover point is right here, that negative 0.75. What was it? Let's see. It was over here. Negative 0.49, excuse me. Negative 0.49, it's over here. Now, this is one of those crossover points, but it's irrelevant. Why? Because it's negative. Remember what we're doing here. We are trying to quantify the performance of algorithms. Algorithms take input and use resources. So what sense does it make to have a negatively sized input, right? We're not looking at, this is not one of our crossover points. Here's the other crossover point. Those two are crossover points, but they're not the relevant ones, okay? So what about the other one? The other root is the positive root, and that is 100.49. That is the crossover point that we observed before. Let me go ahead and move this back to 1 up to 105. Right? And so the crossover point here, right? Again, C here is implicit, C times this, but what I've done is I've fixed C to be 1. Right? And now I'm looking, and now I want to find that crossover point. And so what we can say is that after 100.49, or the next integer, these, because we're all dealing with these integers, because again, these are inputs. We don't care, there's no such thing as a 100.49 sized input. So just go to the next integer, 101. From 101 and beyond, in fact, I'll change the range here to 101 to, I don't know, 150. Right? From that point on, this function will always stay above the other function because of the roots that I just established. Right? After 101 over here, this function, the red function over here, the magenta function, which is n cubed, is always going to be larger than the quadratic function over here. Okay? That's approach 1. And it only worked out really well because I artificially chose those two functions so that I could throw away a root immediately and then apply something that I knew really well how to use, the quadratic formula. That's not always going to work out that cleanly. So that's not the recommended approach. The other recommended approach, approach B, is given two functions that find an inequality that works for some and not. There we go. That is, we will fix and not, and we might have to adjust that and change that a little bit, and find C. Find my constant C. Okay? So again, what I'm going to do is I'm going to go back to the overhead here, and I'm going to go through that approach. Right? So again, we've got f of n is 100 n squared plus 50n. And g of n is n cubed. And what I want to do the exact same thing as before. I want to establish that f of n is less than or equal to c g of n, but I'm not fixing c anymore. C is going to be the variable that I need to find for all n not n greater than or equal to n not. I'm going to fix n not instead as my starting point. So what I'm going to do is I'm going to, the way that I'm going to approach this is I'm going to say, let n not be 0. That's my starting point because I'm not going to start in the negative range because, again, there's no such thing as a negatively sized input. So what I'm going to do is I'm going to start out with the left-hand side here. Write down f of n, which is equal to 100 n squared plus 50n. I eventually want to make it look like something less than or equal to c times g of n. Well, what does g of n look like? Oh, there it is, n cubed. I want to establish that this thing is less than this thing for all n greater than or equal to n naught. Right? Well, it's not that apparent at first, but what I can do is I can make this thing bigger. So this is my goal. This is where I want to end up. So let's go ahead and ignore that for now. But I usually like to write them down because I want to know what am I working towards, right? Well, I'm trying to make this bigger. Again, this is an inequality. As long as I can make this bigger and bigger and bigger until it looks like something like this, then and as long as the inequalities are all true, then I've established this relationship up here. Okay, so let's make this bigger. Well, what's bigger, less than or equal to? What's bigger than 100n squared plus 50n? Well, I do know that linear functions are smaller than quadratic functions, or quadratic functions are bigger than linear functions. So what's to stop me from doing the following? This is less than or equal to 100n squared plus 50n squared. Right? Why? Because n is less than or equal to n squared for all n greater than or equal to n naught. That's not true if for negative values, right? For negative 10, let's negative 10, this is negative 10, and this is 100, right? I guess that's true for some values, but again, negative values are completely irrelevant here, okay? Well, I've made this bigger, and now I can consolidate it to one term. This is now equal to 150 n squared. Now, I've gotten down to one term here, and I've got something that looks suspiciously like a constant. I just need to make this a little bit bigger. This is less than or equal to 150 n cubed. Why? Because n squared is less than n cubed for all n greater than or equal to 0. Right? That's what we call obvious land there. You don't need to establish any proof for that. Right? So for c being 150 and n naught being 0, the inequality holds. And we've established that f of n, for f of n being this quadratic polynomial here, is order g of n. Okay? That's approach B. And that's the approach that I recommend. In fact, I recommend a third approach, which is using the limit method, but that requires calculus. And we don't assume calculus in this course, so I'm not going to go through that. But there are pre-prepared video lectures on that if you are interested in looking at that. Okay? It's as simple as that. All you need to do is make something bigger and bigger and bigger until you get the thing that you're looking for. Now, you can make it too big. For example, let's roll back over here to 150 or 150n squared, right? If I went too far, and I said, well, I'll just make it really, really big, 150n to the fourth, right? I've gone beyond what I was trying to show. And you'll never show that this is less than or equal to 150 n cubed, because that's no longer true. You made it too big. Right? So you can go overboard, but that's why I like to write down my goal here down at the end, maybe in pencil, and then you can go back and erase it. I need to work towards that and make it look like this. And I need to make sure that I don't go over that. Okay? Those are the two approaches. What I want to do is I want to give you a little bit more of an intuition about at least one of those approaches. So the second approach here, I've got those functions again mapped out here. In the first approach, I just simply wanted to find this crossover point, as well as this crossover point and the other crossover point, and then choose the largest root. And then you can say, well, after that, they'll never intersect again because I found all the roots and I chose the largest one. So after that, they'll never intersect again. Oh, sorry. After that, they'll never intersect again after I find this root, and I can establish a simple inequality here that the n cubed is definitely going to be larger, the red one here. Okay. The second approach that I went through was basically, you can look at that graphically as follows. What I was doing is I was changing c, right? I fixed n naught to be 0, so I'm increasing c. By increasing c, you are increasing the slope, or not the slope, but the steepness, I guess you could say, of this. You're increasing the slope by increasing the coefficient. You're not changing the order of growth though. By simply multiplying by a constant, you're changing how steep it is. So let's look at what that might look like. Oops, sorry. There we go. All right. So if I change c to 1.25. That makes it steeper, and it changes the crossover point. The crossover point was at 100.49. Now it's smaller. If I make it steeper still, I'm reducing the crossover point, reducing the crossover point, reducing the crossover point. Now see, now my coefficient here is at 2. And you can continue to do that until your crossover point matches your choice for n naught. My choice for n naught was 0. So I just need to keep going and keep going and keep going until I find a value 10. I think that is fine. Such that I've made it so steep, but now the intersection of this over here is going to be 0. I think 10 works. Right? That's graphically what you're doing when you're making a function larger and larger and larger. Okay, you're just changing that crossover point by fixing fixing your starting point and not, and then making it steeper and steeper and steeper until that last crossover point is over here and matches your choice. Okay. All right. Any questions so far? Okay. All right. So then, you really need to get into this by getting your hands dirty. And that's why that's when you really start to understand these things. You all have the intuition that this function, it looks like it's bigger than this function, and use that intuition, because using that intuition says, okay, that's what I want to show. And now I just need to apply these mathematical inequalities and actually come up with it. So practice is where you really understand this stuff. It's just like coding. Mathematics is really like coding in that practice makes perfect, and practice makes you understand this kind of stuff. So what I did is I just pulled a random computer science homework here off the internet. And we've got a bunch of random expressions and values here. Here's our first, so I'm going to switch back over to the overhead here, and let's start working with these things. So the first one, in case you missed it, was 0.000 n cubed. Oh, there was a 5 in front, plus 0.025 n. Right? Now, all you have to do here, the intuition, is all you have to do is look at this and say, which one is the highest order of term? Because again, the whole point of big O analysis is that it allows us to ignore constants, and it allows us to cross out and ignore the lower order terms. Well, we've got a constant here, we've got a cube here, and we've got a linear term here. So clearly the cubic term, even though it's got a very, very small coefficient, that's still going to dominate as n tends towards infinity. So this homework tried to trick you by rewriting it. Well, what I'm going to do is I'm going to rewrite it so that it becomes obvious. A polynomial like this is properly written with the highest order terms first, then the next lower order term, then the next lower order term. So degree 3, there is no degree 2, or you can say that there's a degree 2 here, but the coefficient is 0. Linear degree 1, and a constant degree 0. Right? So clearly, this is the highest order term here. In other words, our intuition tells us that we want to show that if this is f of n, we want to show that f of n is big O of n cubed. In other words, we want to be able to cross off these lower order terms, cross off the constant term here, and ultimately we're left with the most important thing here, n cubed. Right? Let's show that a little bit more rigorously. So I'm going to go ahead and establish this 0, 0, 0, 1 n cubed, right? Plus 0.025 n plus 5. Right? And again, you could go down here and you want to show that this is less than or equal to some c n cubed. Right? Now that we've established how to do this, this should be pretty straightforward. You can go ahead and make all of these terms immediately n cubed. Right? This is less than or equal to, it's not equal to, but it is less than or equal to 0, 0, 1 n cubed plus, I can make a linear term bigger by making it into a quadratic term. I can go ahead and skip all the way to a cubic term, 0.025 n cubed plus 5 n cubed. Sorry, cubed. There we go. For all n not n greater than or equal to 0. Right? That's certainly true. Again, you're in obvious land. N is less than or equal to n cubed for all positive n. That's not necessarily true for negative n, but for all non-negative n, it's certainly true. And certainly n squared is less than or equal to n cubed, and certainly a constant, 3, is less than or equal to n cubed. right? Those are all, this is what I call obvious land. You don't need a mathematical proof for this, okay? So now we can collapse these all together. This is equal to 5.0251 n cubed, which is exactly what we're trying to get at. There's some constant here times n cubed. Right? And the inequalities follow all the way through. Less than or equal to, in other words, transitively less than or equal to. So for C being 5.0251 and n not being 0, the inequality holds, and you can finish out the sentence there that that this thing f of n is going to be big O of n cubed. Okay? All right. The next one here is going to be 500 n plus 100 n to the 1.5. So it's still a polynomial here. This is like a linear times a square root function plus 50 n log base 10 of 5, right? Or sorry, that's an n there, okay? So again, intuition. What is the highest order term here? Well, we've got a linear term. We've got a larger than linear term here. This is not all the way to a quadratic term, but it's certainly not a linear term. It's somewhere in between, right? So definitely this one is bigger than this one. What about this one over here? N and log base 10 of n, right? So this is what we call quasi linear or quasi polynomial in general, where you've got a linear term, but then you're multiplying it by a logarithmic term. Those logarithmic terms cannot be ignored. Those are monotone increasing functions. They are growing functions as n tends towards infinity. But if I chop off, if I set up a ratio here and I say, well, this is n to the 1.5 and this is n. So what about n to the 0.5 versus log base 10 of n? Right? Which one of these has a higher order of growth? Right? Now, your intuition might not be all that obvious on this one. Hopefully it is. But any polynomial term is going to grow larger than a logarithmic term. Okay? Logarithms are very, very slow growing functions. It doesn't matter if it's n to the 0.000000, a million zeros there, 1, versus this logarithmic function. This is going to have a higher order of growth, right? Because it is a polynomial function. It just has a polynomial of a very small degree, but it still has an order of growth that is larger than any logarithmic function. Okay? So that tells me that this is probably the dominant term here, right? And so that I want to show that f of n is big O of n to the 1.5. You can't ignore that 0.5. If I just said that it was n, that would not be right because this is smaller. Now I could say that, yeah, it's going to be order n squared. That's technically correct, and I guess technically that's the best kind of correct, right? Being technically correct, but we don't. That's not what we want to show. We want to establish what is the highest order term within this thing. So yes, this is correct, and you could get away with that. But what I want to do is I want to show this. Okay. So let's go ahead and give myself some more room here. 500. Actually, no, let me rewrite this. Sorry. I'm going to write the highest order term over here. 100 n to the 1.5 plus 500 n plus 50 n log base 10 of n. I'm sorry. This has a higher order of growth than this one, but I've rewritten it now twice, so I'll go ahead and go with this. All right, this is less than or equal to. Now I can make that n to the 1.5 because n to the 1.5 is larger than n. So 100 n to the 1.5 plus 500 n to the 1.5. Right? But now you've got to be careful here. If I go all the way up to n to the 1.5 log base 10 of n, then I've done the thing that I did that I illustrated. I've gone too far. I made the mistake that I illustrated before, where you go from n squared all the way up to n to the fourth, and now you're never going to be able to establish that that's less than or equal to n cubed because you've gone beyond that. Okay, so that's not what I'm going to want to do here. All right, let's go ahead and keep that term for now, n log base 10 of n. Right? Okay, this is true for all n greater than or equal to n 0. Right? So I can combine those into one term, but this, I still need to take care of this thing. Okay, so off to the side, let's go ahead and establish a relationship between 50n log base 10 of n and n to the 1.5. In other words, I want to show 50n log base 10 of n is less than or equal to some constant, and I'll go ahead and go with c here, even though it's not the same constant as I was working with up over here, of n to the 1.5. Okay? Well, like I did before, if I ignore this n, and I can chop off this 1 right here. In other words, I only have to focus on log base 10 of n and the other term there, right? Where basically I'm changing the question here. I want to show that log base 10 of n is less than or equal to some constant n to the 0.5. Right? In other words, this is square root of n right here. Okay. So I could go ahead. I could go ahead and go back to approach A, where I find the crossover point here, or I could start reasoning about this a little bit. Log base 10 of n. When does that become 1? Well, that becomes 1 when n is 10, right? What about the square root of 10? Right? That's 3 point something something something, right? So this is 1 and this is 3. If I graph these out, I could find that for all n greater than or equal to 10, right, that this inequality holds, right? And that's all I need to really do. Again, you're kind of in obvious land at that point. Let's see, 100, that's going to be 10. The square root of 100, that's going to be 10. So yeah, you got to be careful. Let's actually go back to Wolfram Alpha over here, and let's graph these out to look what see what it looks like. Let me go ahead and create a new one. So here we go. Log base 10 of n. There we go. And the other one was square root of n. Square root of n. There we go. And I'll just go 0 to I don't know 500. Let's look and see what it looks like. All right, there we go. So there's the square root of n. After 0, it looks like that we're now. If I want to zoom in here, then let's go ahead and go down to 1, say, and let's look at what that graph looks like from 0 to 1. Right? And square root of n is always going to be positive. Now, what I wanted to show this graph to you to show you one of the common gotchas. What if I kept my n naught at 0 here? Is log base 10 of 0 well defined? No, it's negative infinity. So I cannot start at 0. I have to jump all the way up to 1, at which point, if I look at all the values 1 and beyond, right, then that square root should dominate. Right? That's always going to be greater. Right? So transition back here. I can no longer use 0. But I can go ahead and go larger for all n greater than or equal to 1, because log base 10 of 0 is not well defined. Right? And my constant here can be 1, because it's always going to be true after 1. Right? It's always going to be true after 0, but again, it's not defined at 0. So let's plug that back in up here, right? That I can say that, okay, that was our aside there. And we'll continue our inequality down here. Less than or equal to, now let me go ahead and combine those two into one term here, 600 and the 1.5. Right? And by this analysis down here, what I can say is that this is less than or equal to 50 n times n to the 0.5 for all n greater than or equal to 1. Okay? Now, these two can be combined here. Again, I was only focusing on that logarithmic term to establish that it was less than or equal to the square root of n. I did that because I knew that when I replace that with the square root of n and I multiply these together, I add their exponents and I get that this is equal to 600 n to the 1.5 plus 50 n to the 1.5. And that allows me to match with this one, and this is equal to now 650 n to the 1.5. So for C being 650 and n being, or n naught, excuse me, being 1, the inequality is established. Again, this is not tight. There are an infinite number of combinations of C and n that will work for this equation. Right? There are an infinite number of possibilities. I just had to find two that actually worked and show this and establish this inequality, the series of inequalities. Okay. So let's take a look at another one. Let's go ahead and fast forward through a couple of these. So if I look at this third one here, what's the largest order term here? Well, I've got an exponent of 1, an exponent of 1.5, and an exponent of 1.75. So clearly, it's going to be this one right here. On the fourth one, and you can go through again, the same process as before to establish, and this one would be even easier than the last one because you can increase 1.5 to 1.75, collapse those down. You can increase n1 up to 1.75 and collapse that down. Here's where it becomes a little bit less obvious. N squared and a logarithmic term, and n and a squared logarithm term. Right? That's n times log base 2 of n times log base 2 of n. Right? So this n matches with one of these n's, and I can then focus on just that it's n log, and then one of these logs, it cancels out kind of with this one. So all I'm really looking at is whether or not n is greater than or equal to log n, and that's certainly not true. The one log n term here does not make up for the linear term over here. Right? So clearly, this is going to dominate versus this one, right? Because the linear function, the polynomial here being squared is a lot bigger than a logarithm being squared. Okay. Here's an interesting one, and I'm going to actually simplify this, and we're actually going to do this over here. N log base 3 of n and n log base 2 of n. Okay, so I'm going to simplify it by just focusing on those two logs. Log base 2 of n versus log base 3 of n. Right? Now, you might have an intuition here. You can go ahead and plug in some values here. Say, well, 4. Log base 2 of 4 is going to be 2. Log base 3 of that is going to be even less. It's going to be 1 point something. So you could say, oh, well, log base 2 of n, that probably grows faster. But it works both ways. Right? What I'm going to do is I'm going to show that, I'm going to demonstrate that 1, log base 2 of n is big O of log base 3 of n. And I'm also going to establish the other way around. Log base 3 of n is order log base 2 of n. Right? Both of these things are true. Now, we're not going to get into it in this course, but this establishes a theta relationship. That if they're both tight, if they're both the same order of growth, then it's not big O of each other. O is omicron, if you remember, but it's written the exact same as O. So this actually establishes that these are theta of each other, and that you would actually write theta instead of O. Right? But again, that goes beyond the scope of this course. Let me go ahead and show you this first one. In fact, it's going to be the exact same proof in both of these. I want to show that log base 2 of n is less than or equal to c times log base 3 of n. Right? Except we already have a tool to do that directly in one step. Right? Observe. Log base 2 of n is equal to, here's our change of base formula. Remember that the log base A of n can be changed to any other base, log base B of n. All you have to do is divide out by log base B of A, which is a constant. A is constant, B is constant. So all we have to do is apply this change of base formula here to get it to look like the right-hand side. Log base 3 of n divided by log base 3 of 2. Now, you can pull out your calculator and figure this out and see what it looks like. But basically, all I want to do is I want to show that this is less than or equal to, in fact, it's exactly equal to c log base 3 of n, where n is greater than or equal to, now again, here you have to be careful, don't establish it at 0, or establish it at 1, because logs of zeros are undefined, they're negative infinity, and for c being 1 over log base 3 of 2. And again, you can pull out your calculator if you really want to and figure that out. I'm not going to, just leave it in symbolic form. Symbolic form is much cleaner instead of writing, and I'm sure that it's irrational, so you technically can't write it down anyway because it goes off with an infinite number of digits. I can do the same thing with the other part, right? I can establish that log base 3 of n is equal to log base 2 of n over log base 2 of 3, right? So for n greater than or equal to 1, and c being, now this is the other one, log base 2 of 3, right? Then I've established this relationship right here, right? That tells you that logarithms have the same order of growth. Linear functions have the same order of growth, right? And this harkens back to something that we were discussing earlier. Remember last time when we talked about what's the input size of a number? Well, it's the number of digits that it's required to write that number down. Or it's the number of bits required to write that down. Now the question here is, does it matter? No, it doesn't. It doesn't matter if you have binary computers that count in zeros and ones versus humans that count in base 10 versus octal versus hexadecimal or versus some weird alien system that's base 5 or something like that, right? All bases are the same to within a constant. So it doesn't matter if you are writing stuff down on a paper in base 10 or executing it on a computer in base 0, or base 2, excuse me. There is no such thing as base 0. It's the nothing mathematics. All right. So it doesn't matter if it's base 10 or base 2 on a computer because all of your operations are going to be proportional to each other. Right? It just means that the binary operations, there might be a few extra steps, but they're all constant steps. And you can translate back and forth. You can translate base 10 into binary and binary into base 10. You do this all the time. You do this as a matter of course in Computer Science 1. Right? And it's all because of asymptotics and the change of base formula. Okay? All right, I want to do a few more. Let's just hurry through the rest of these because I have ones that I want to do. So base 8 and log of log of log. These can be tricky here, but logarithms are slow-growing functions. So if you take the logarithm of another logarithm, you make it even smaller. So clearly, this is going to be the dominant term here. N squared and n, well, clearly the quadratic here is going to be larger. It doesn't matter that the coefficient here is much smaller than the coefficient over here because the whole point of big O analysis is ignoring those constants. Same thing here. It doesn't matter if you switch those around. It's still going to be dominant over here. Over here, this is the dominant value. Let's see, n log base 2 of n, and then n log squared. This has an extra logarithm in it, and logarithms are monotone growing functions. So this one would be the dominant term. Right? We're doing homework for some other class here. Hope maybe they can find this video and then they get some free answers or something. Over here, we've got n log n. It doesn't matter what the base is. You can always ignore the base. That's why in computer science, we always write log n. We don't explicitly write the base because we know that it doesn't matter. You can always change a base formula. You can always change them. But then the cubic is definitely larger than n log n. And the linear term here is definitely smaller than the cubic term. So definitely the cubic term is the dominant term here. A single log versus a log of a log. definitely the log is going to grow faster than taking the log of a log. Okay. I'm going to fast forward here to a summary. There we go. And these are all these are some of the major classes of functions. For example, you can have that come up all the time with algorithm analysis. You can have a function, or you can have an algorithm that just computes a formula, and that's going to be constant, right? It doesn't matter how big of an input is. If you do a constant number of operations, regardless of the input size, then it's going to be constant. You have logarithmic. We'll view this again next time when we revisit searching and sorting. Binary search is logarithmic. A linear search is linear. A linear search is linear. That's why we call it linear, right? If it's just a linear term. Quasi linear. Quasi being almost, like Quasimodo, almost a man. Here we've got quasi linear, almost a linear function because I've got n times a log of n. Quadratic, of course, would be any polynomial of degree 2. Cubic, polynomial of degree 3, or in general, if you've just got any polynomial here, you can say that it's order n to the k. It's a polynomial function. You've also got exponential functions and super exponential functions, and not all of those are created equally. So what I want to do is since that assignment didn't have any examples using exponentials, I want to do some more examples using more examples here using exponentials. Well, what about 2 to the n versus 3 to the n? Right? Now, again, if you graph this out, you'll immediately see that even at 1, right, 2 to the 1, 3 to the 1, 2 is less than or equal to 3, and so we've already established that that 2 to the n is O of 3 to the n. Right? You just have to be careful here. Because at 0, of course, they're equal. At 1, they've started to diverge from each other already. 2, of course. 3, that'd be 8 versus 21, 27, etc. So again, what I like to call this is obvious land. This does not really require a proof. Right? You can show that 2 to the n is less than or equal to 3 to the n for all n greater than or equal to 0. Right? But what happens when you start messing around with other functions? So for example, what about n 2 to the n versus 4 to the n? Right? Now, you might be tempted to graph these out and say, well, what happens at 1? Right? Well, at 1, this is 4 and 1, and this is 2, so that works. What about at 0? Right, well, that also works. This is 0 and this is 1. What about at 2, though? 2 times 2, that's 8, and 4 times 4, oh, that's 16. So yeah, that seems to kind of work out, but you do have to be careful about it, and we'll see why you have to be careful about it in the next example. But I still need to establish this mathematically, right? A graph is not a proof. A graph can help you with the intuition and say, oh, well, that function is clearly larger than this function, so that's what I should be showing. In other words, I want to show that n to the 2n is big O of 4 to the n. Right? And by the way, the other way around does not work. There is no constant and there is no n such that you can establish that 3 to the n is big O of 2 to the n. Not all exponentials are not created equal. Okay. All right, so let's go ahead and establish this. N to the 2 to the n, I want to show that this is less than or equal to some c times 4 to the n. Right? So let's go ahead and do it over here. N 2 to the n is less than or equal to what? Right? Well, again, you can say another part of obvious land here is n is less than or equal to 2 to the n. Okay. Hopefully that's obvious, and that therefore I can change the first term here to 2 to the n. This is less than or equal to 2 to the n times 2 to the n for all n greater than or equal to. And again, you have to be careful here. 2 and 2, that works. 3 and 3 is less than or equal to 2 to the third, which is 8. Yeah, that works. So it works for all n greater than or equal to 0. Right? Okay, Well, I might be tempted immediately to use my algebra skills here and and come up with two. Well, when you multiply these together, they're the same base, so I come up with n plus n. Well, that's equal to 2 to the 2 to the n. That doesn't very much look like 4 to the n yet, but it is actually, because you can take this down. And so you can go that route. Or you can realize, well, wait a second. Actually, that's what... yeah, that's what we're actually going to want to do, right? Yeah, never mind. Sorry. I was thinking of something else. I was thinking of the next example. So this is going to be equal to 2 to the 2 to the n, which is equal to 4 to the n. Right? Now, if I had done something like n is less than or equal to 3 to the n, then obviously I would have overshot and made this even bigger than 4 to the n. But I've established that this is less than or equal to this. So for c being 1 and for n not being 0, the inequality holds. Right? And you just need to be a little bit more formal about it, okay, by writing it out, maybe a couple of sentences there, okay? What about if I mix polynomials as additive terms? Versus, what do I want to do? Let's see, versus 3 to the n. All right, there's my, here's the last example for the day. Now this one is exponential, but of a higher base, but this one has a polynomial term over here. Right? But my intuition tells me, and if I graph it out, my intuition will be confirmed, that I want to show that 2 to the n plus n squared, and you can rewrite this because higher order terms come first, right? Biggest things first, is going to be order 3 to the n, okay? Now here's my first attempt, all right? What was my, yeah, okay, I could make this even simpler, I think, than what I had done before. Let's go ahead and go with, well, here's my first attempt. So 2 to the n plus n squared is less than or equal to, well, let me go ahead and make this term look like this term by making it bigger, right? 2 to the n plus 2 to the n. Right? N squared is certainly less than or equal to 2 to the n, but you have to establish for what values, okay? Let's try it for 1. N squared and 2 to the n for n values of 1. Well, this is 1 and this is 2. Okay, well, that inequality is established. But 2, that's 4, and that's 4. Okay, that's still less than or equal to. 3, this is 9, and this is 8, right? So, no, it does not work. That's not times. That's inequality doesn't hold. But if I go up to 4, now this is 16, and this is 16. If I go up to 5, now this is 25, and you can see that at that point they're separated. So, yeah, you can write this down. You just have to be very careful about what your n naught is for all n greater than or equal to 4. Right? So be careful. Don't lose the forest for the trees here. Okay? All right, let's go ahead and, well, collapse these. Well, if this is 2 to the n plus 2 to the n, that's twice 2 to the n. Right? Okay? And again, it might be helpful for you if you establish what you want to show down here as this is a roadmap and this is your destination down here. This is c 3 to the n. Well, I got it down to 1 term and my c over here is 2. All I need to do is make it a little bit bigger by returning to obvious land and saying that 2 to the n is less than or equal to 3 to the n for all n greater than or equal to 0. But I've already established a larger n over here, which is still true for. So this is less than or equal to 2 times 3 to the n for all n greater than or equal to 4. There. For c being 2 and n not being 4, the inequality is established. Okay? All right. Hopefully we'll get a lot more practice. What I would suggest doing is, again, this is all on your final homework, which is due in a few weeks. But everything that we're covering since algorithms and algorithm analysis, that's covered on your final homework. I would encourage you to work along with it. And then when questions pop up, ask them in lecture or on Piazza or in office hours. Don't wait till the last moment to, okay, well, I'm looking at this material. Okay, I think I've absorbed it, but then you wait a couple of weeks and get started on the homework, and then you forget it all. Okay. What we're going to do next time is wrap up algorithms and algorithm analysis by looking at a few more examples and establishing a few more asymptotic inclusions. We'll revisit all of this in terms of searching and sorting that you've seen before. We've already looked at selection, sort, and linear search. We're going to revisit binary search and quick sort, and we're going to look also at two other sorting algorithms, maybe insertion sort and merge sort, and we're going to look at another way of analyzing algorithms using something called the master theorem. It's for recursive algorithms. Now that you've had your review of recursion from lab yesterday, we're going to revisit recursion. Okay? All right, let me check one last time. Were there any questions that popped up? Does not look like it. So, have a good weekend. Make sure that you are getting that your design document is due. Your final draft, draft, not the final version, but the final draft is due this Friday by midnight. Make sure that you're handing that in. Okay. Otherwise, have a good weekend.